Mathematical formalism of quantum mechanics. We know mathematics is the fundamental tool we use in physics. Okay, so mathematical formalism of quantum mechanics deals with the development of mathematics for representing the particle in a quantum mechanical state. Okay, so in a classical mechanics, we know a particle of m is moving with certain velocity v, then there will be different properties like force, it is a vector, momentum, it is also a vector, and we can represent this position by a position vector. So this is a real space, and in real space we use these vectors to represent the particle properties. So we have a coordinate system x, y, z. Okay, so we represent the position of the particle by a vector in this coordinate system, right? So this is a combination of x, y, z, and we represent this as r vector. So this have a magnitude and a direction. And the basis of this coordinate system is x cap, y cap, and z cap. Three unit vectors are there. They are orthogonal to each other, right? So any vector we can represent by using these bases, that is 2x cap plus 3y cap plus 9k cap. Okay, so any vector can be represented by using this basis. That is, in general, a vector can be represented as a combination of ai, ei cap, where ei cap are the basis and ai are the constants in the real space. So from this idea, we can say vector is a linear combination because there is a summation sign of basis vectors. Now, in the case of a quantum mechanics, when particle of mass m, if it travels with a certain velocity, its wave nature will dominate. That is, the particle become a wave. So we already discussed this particle can have in different states in a 1D box like this one. So it can form a stationary wave like this one inside a box, and this one inside a box, and etc. Okay, so this particle can exist in different states. So these different states we represent by wave function psi1, psi2, etc. So in general, there is a coordinate system, or there is a space. Actually, this is a 3D space. Similarly, we need a space in quantum mechanics. In that space, we can represent all these states. So this will be psi1, psi2, psi3. And that space is called Hilbert space. Similar to real space, we use Hilbert space in quantum mechanics to represent the particle. So the basis in the Hilbert space will be psi1, psi2, psi3, etc. That is, the general wave function is a linear combination of different wave function, that is ci, psi I. And we discussed the total probability of finding a particle is 1. Therefore, modulus of these terms c1 square modulus of c2 square plus modulus of c3 square should be equal to 1. So here I am limiting this to only 3 vectors, psi1, psi2 and psi3. So this modulus square of these constants should be equal to 1. Then only it can represent the physical particle. Therefore, the wave function psi will be equal to c1 psi1 plus c2 psi2 plus c3 psi3. This we already discussed in the earlier classes, right? And what is this Hilbert space? This Hilbert space should satisfy some mathematical rules. The first rule is, it is a linear space. That means it satisfies the vector addition rules and the scalar multiplication rules. And second one, if phi and psi are two scalars in Hilbert space, then it should satisfy the following condition. One is a condition regarding the scalar product, that is inner product, that is phi psi is equal to phi psi star. Another one, it should satisfy psi a phi 1 plus b phi 2, then it should be equal to a phi psi 1 plus b psi phi 2. Another condition, psi scalar product of psi should be equal to mod psi square and should be always greater than or equal to 0. There is no negative values. So these are some properties of vectors in Hilbert space. And this one, the Hilbert space is complex one also. In the earlier case, we discussed some wave function, that is at time t, we got some root 2 by L sine pi x by L into e raised to minus I even t by h cross. See, exponential term is there. That is, it is a complex number. Okay, so Hilbert space is generally a complex number, or we can say it is a linear vector space over complex numbers. And in the early classes, we discussed some properties like orthogonality, normalization. So these vectors are orthonormal vectors. So I think you are remembering all those ideas, right? And in quantum mechanics, we are dealing with two things. One is states, that is represented by vectors, psi 1, psi 2, etc. And we have operators. So what is the use of this operator, or what is this operator will do? Actually, this operator is a measuring device. It acts like a thermometer or weighing machine, etc. How? Why I am telling like that? Because suppose an operator is operating on some state. Suppose this operator is this operator operating on the state means thermometer is using to measure its temperature. So what we get? We get the temperature and the state. Or like measuring the air pressure inside a tire. So what we will get? We will get the air pressure and the state. When we are measuring the air pressure, some air inside the tire will goes into the gauge. So the pressure level inside the tire will slightly differ after the measurement. So we get another state, that is psi 2. These two possibilities are there. On measuring a state, its state itself slightly changes, or sometimes it will not changes. If this is the case, then we call lambda is a eigenvalue. That is, this is our Hilbert space. In this Hilbert space, this one represents state of a system, and now we are measuring some property of this system, that is some operator is operating on this state. So we get another state. So this operator can transform one state vector to another. And some examples of operators we are using in quantum mechanics are position operator, that is x itself, and another one is momentum operator, that is equal to minus I h cross dou by dou x, and energy operator, that is Hamiltonian operator, that is equal to I h cut dou by dou t. So these are some examples for operators. So this operator, for example, this Hamiltonian operator will operate on certain state and it will give energy and the state itself. Here this one is an eigenvalue operator. That is why the wave function is not changed. Same wave function we will obtain after the measurement. And the operators we use in quantum mechanics are all linear operators. What is this linear operator? If O is an operator, a linear operator, then it should satisfy the following criteria. That is, if this operator is operating on a state, that is a psi, where A is a constant, there is this operator operate on the state on its right hand side, and here it is A is a constant, so it can be written as operator psi. And second condition, if operator is acting on a state, combination of states, that is A1 psi 1 plus A2 psi 2, then it should be equal to A1 operator psi 1 plus A2 operator psi 2. If it satisfies this condition, then we can say it is a linear operator. Then definitely you will have what is a non-linear operator. I tell you one example, that is a square operator. Why square operator is non-linear operator? I tell you, suppose there are two states, psi 1 and psi 2. So this square operator, I am calling it as A, and this operator is operating on psi 1. So what we will obtain? We will obtain square of this function, that is psi 1 square. Similarly, this operator is operating on state psi 2. So what we will obtain? We will obtain psi 2 square. Now I am going to operate this operator on psi 1 plus psi 2. So what is the square of A plus B? This is like A plus B. A square plus 2AB plus B square. So we get phi 1 square plus 2 phi 1 phi 2 plus psi 2 square. And here this operator is not operating like this one. If it is operating like a linear operator, then it will be equal to phi 1 square plus phi 2 square. But here we obtained phi 1 square plus 2 phi 1 phi 2 plus phi 2 square. Okay, so this is definitely not a linear operator. That is, here this operator can be taken into the bracket. Okay, but here it is operating over the total time, that is phi 1 plus phi 2. So this square operator is definitely not a linear operator. Another example, a sine operator. That is, if an operator A, which is sine operator, which acts on a state psi 1, then it will give sine of that function. So this operator is acting on another state also, that is psi 2, then it will give sine of that function. Now we can check if this operates on a state psi 1 plus psi 2, then what will be the answer? That is sine of phi 1 phi 2. Sine of this function is similar to sine of A plus B. That is, this is equal to sine phi 1 cos phi 2 plus cos phi 2 sine phi 1. Okay, this is not equal to adding these two terms. That is why it is called non-linear operator. If it is a linear operator, the answer should be sine phi 1 plus sine phi 2. But the answer is this one. Okay, so this is not a linear operator. Another example, square root. The operator is a square root. That is, if this operator operating on phi 1, it will give root of phi 1. And if it is acting on another state, phi 2, it will give root phi 2. So, if this operator is acting on a combination of these states, then what will be the result? Root of phi 1 plus phi 2. This is not equal to an operator operating on the state first, then it is operating on the state. That is a linear operator. So if it is operating like this, then what we will get? We will get root phi 1 plus root phi 2. But see, these are different. Okay, so this is also non-linear operator. If it is a linear operator, we will get this result. Okay. Now we can discuss some examples of linear operator. In quantum mechanics, every operator is linear operator. What are these operators? We know the position operator, that is x cap, that is equal to x, and the momentum operator, that is equal to minus ih cross dou by dou x, and the energy operator, that is Hamiltonian operator, that is ih cross dou by dou t, and the angular momentum operator Lz, etc. Every operator we use in quantum mechanics are linear operator. Suppose a Hamiltonian operator, energy operator, is operating on some state phi 1 plus phi 2 plus phi 3. Then how this will operate? This Hamiltonian operate on this one, then it will operate on this one, then it will operate on this one. So when expanding this function, it will look like h cap phi 1 plus h cap phi 2 plus h cap phi 3. So when this Hamiltonian operator operates on these states, it will give corresponding energies E1, E2 and E3, right? So this is how a linear operator operates on its state vectors. Hermitian operator. I think you are familiar with this term, Hermitian. You know Hermitian matrix. What is a Hermitian matrix? For a Hermitian matrix A, its conjugate transpose will be equal to that itself. Okay, this is the definition of a Hermitian matrix. Similarly, for a Hermitian operator, this become operator, so its conjugate transpose of this operator will be equal to that one itself. That is called a Hermitian operator, or we call it as a self-adjoint operator. And if a Hermitian operator is operating on some state, it will give an eigenvalue and state itself. And here this eigenvalue has certain property, that is this eigenvalue will always a real value. The examples of Hermitian operators are quantum mechanical operators, that is Hamiltonian operator, momentum operator, position operator, angular momentum operator, etc. See, suppose a Hamiltonian operator is operating on some state. What will you get? You will get the energy and state, and this energy is always real value. That is why I told you the Hermitian operator always give a real eigenvalue. Okay. Dirac notations. Actually, we already discussed about Dirac notations, right? Then also we can discuss once again. First one is a state vector psi is represented as ket psi. It is called as ket, right? And the psi star, the conjugate of complex conjugate of a state vector, is represented as bra psi. See, it is like a bracket. See, this is a bracket. Bracket is look like this one, and we separated this as bra and ket. Okay, that is, this is ket and this is bra. See, it's a bracket. Okay, third one, ket a psi. Here this a is a constant, and if you are taking this constant from the ket notation, then it will be look like this one. And the fourth one, bra a psi. And if you are taking this constant a outside of this bra notation, then it will be is complex conjugate. Fifth one, ket a, whereas a is operator, a psi will be equal to a operator ket psi. And bra a operator psi is equal to a dagger, that is conjugate transpose of a operator bra psi. And this will be represented as bra psi a dagger. Sixth property, bra psi I ket psi j is equal to delta ij. That means this is equal to 0 for I not equal to j and is equal to 1 for I equal to j. That is, this is the condition of orthonormal. That is, it is same time orthogonal and normalized. And seventh notation is operator, expectation value of operator. So that is equal to integral psi star o psi dx, or we can represent this as bra psi o psi. So these are some common direct notations we use throughout the quantum mechanics. Operator algebra. I think you are familiar with the algebra. That is basic mathematics, right? So in algebra, we know a plus b all square is equal to a square plus 2ab plus b square. And we know e raised to a into e raised to b is equal to e raised to a plus b. And ab square is equal to a square b square. Now we are going to discuss about operator algebra. The operator algebra is different from our conventional algebra. That is, for example, we have two operators. One is a operator and another is b operator. Then operator a cap plus b cap all square will not be equal to a cap square plus 2a cap b cap plus b cap square. It will not be equal to this one. Okay. And another case, if e raised to a operator into e raised to b operator, this is not equal to e raised to a operator plus b operator in operator algebra. And if a b is there and square of this is not equal to a cap square b cap square. So definitely the operator algebra is different from our algebra. We will discuss how these operators will operate. Exponential operator. Let us consider an operator, and if this operator operates on some state psi, then we will get an eigenvalue and that state itself. Okay, then what will be e raised to a? That is, what is the value of exponential of this operator? From basic mathematics we know e raised to x. What is e raised to x? That is equal to 1 plus x square by 2 factorial plus x cube by 3 factorial, etc. Right? In a similar fashion, we can write e raised to a operator, that is equal to 1 become identity plus a operator plus a operator square by 2 factorial plus a operator cube by 3 factorial, etc. So if this operator operates on some state psi, that is equal to I plus a operator plus a operator square by 2 factorial plus a operator cube by 3 factorial plus etc. into psi. So you know this is a linear operator. So each of this term operates on this state. So we get e raised to a operator psi is equal to 1 plus, when a operates on psi, it will give lambda, plus when a square operates on psi, it will give lambda square, that is lambda square by 2 factorial, like that, that is lambda cube by 3 factorial, and it will give the state as itself. And here you see this is equal to, that is e raised to a psi is equal to e raised to lambda psi.